Okay, welcome to lesson 4. Now the focus of this lesson is electronegativity. It's probably the first time you've heard this term, electronegativity, but it's a very important fundamental chemistry concept. We'll be talking a lot about electronegativity in the bonding topic, the next topic. But in a nutshell, electronegativity is the tendency for an atom to attract electrons. Now those electrons specifically are electrons that are involved in bonding. So we can only really discuss electronegativity within the context of electrons that are involved in bonding. Now I also know that you have not studied bonding to a great extent. Some of you probably haven't studied it at all. So just to briefly explain what the positioning, I guess, of the electrons in a bond. If we look at a water molecule, H2O, now a water molecule is made up of 1 oxygen and 2 hydrogens, and the thing that holds the oxygen to the hydrogens is in fact a pair of electrons. When the hydrogen atom and the oxygen atom form this connection, they share electrons, but they position them between the 2 nuclei. So effectively we have an oxygen nucleus there, a hydrogen nucleus here, and electrons, a pair of electrons in between, which are, as you know, negative. So this positive, negative, positive arrangement is the glue that holds these atoms together. It's the glue that holds these atoms together. It's a result of the attraction between opposite charges, positive nucleus and the negative electrons. Now, those electrons are not necessarily shared perfectly equally. In this diagram, I've shown the electrons to be right in the middle between the 2 atoms. Now that's rarely the case in actual fact. In the case of water, the electrons are in fact much closer to the oxygen. And the fact that they're closer to the oxygen, that's due to this concept of electronegativity, because oxygen has a higher electronegativity. It has a higher attraction for the bonded electrons. Okay, now you need to be able to make decisions about electronegativity. You need to be able to pick eventually where the electrons are going to be, whether they're closer to the oxygen or closer to the hydrogen. Another way of putting this term is to say that it's really a description of how fair the sharing is. Which atom gets a bigger share, which atom gets a lower share. That is based on their electronegativity. A large electronegativity means that the electrons are pulled strongly towards the atom. And then atoms that have large negative electron affinities are usually those that end up having large electronegativities. Electron affinity was a term that was first introduced in atomic structure. We didn't spend a lot of time looking at electron affinity, but we said that it's the exact opposite of ionization energy. So the electron affinity equation for something like fluorine would be very much like the ionization energy equation, but it's the energy involved in gaining an electron. This time, of course, it would form a negative ion. So this is the equation for the electron affinity for fluorine. Okay, they have to be gaseous atoms again. But see, an electron is being gained. Ionization energy, the electron was usually on this side, it's being lost. But affinity is the electron being gained. So this statement that atoms with large negative electron affinities means that when this equation here occurs, the large energy value implies that the reaction occurs really easily. So in other words, it has a very strong attraction for the electrons. And that's also a contributing factor to the large electronegativity. All right, so electronegativity is the tendency to attract bonded electrons, the relative attraction for bonded electrons. You will need to memorize this definition. So the trends, here are the trends shown in this slide of the periodic table. And we've got an increase in electronegativity from bottom to top, and an increase in electronegativity from left to right. So the atom that will have the highest electronegativity, you can see the values are shown, is fluorine, top right-hand corner. Why don't the noble gases have electronegativity values? I'll let you think about that. We'll discuss that in class. Following this pattern, francium, bottom left, has the lowest electronegativity value. These values are called the Pauling electronegativity values, and these values are also given in the IB data booklet. And you're expected to be able to use these values. But in addition, you're expected to be able to explain why the electronegativity increases from bottom left to top right. So there's an increase in EN like this. Typical questions in the exam ask students to make judgments about electronegativities of adjacent atoms. You know, why selenium has a higher electronegativity than arsenic. Why sulfur has a higher electronegativity than selenium. Students are expected to be able to make those sorts of judgments. The pattern's not perfect. There are always exceptions to the pattern. And so the sorts of questions that students will be asked will be fairly obvious questions, not some of the tricky little exceptions. Okay, so why does this happen? So as you go down a group, looking just at the group trend, as we go down a group, we know that the electrons are further from the nucleus. They're further from the nucleus because we have an increase in the number of shells. And so, for example, when you go from fluorine to chlorine to bromine down the periodic table, the electrons are going to be further and further away from the nucleus. This means there are more and more inner shells, which means the outer shell electrons are better shielded from the nuclear charge. Essentially, this means that they're not going to be as attracted to the nucleus. And for that reason, we say the electronegativity decreases. Because remember, electronegativity is the attraction for bonded electrons. Electronegativity increases from left to right across the period. Now, there are two ways that we can explain this. We can say that as the nuclear charge increases as you go across the period, so for example, remember sodium on the left and chlorine on the right, the nuclear charge, and if we're talking about the effective nuclear charge for sodium is 1+. Remember, effective nuclear charge is equal to the number of protons minus the number of inner shell electrons. So 12 protons minus 10 electrons gives us an effective nuclear charge of 1+ for sodium. Chlorine has an effective nuclear charge of 7+. That's element number 17, so there are 17, try that again, there are 17 protons, and it has 10 electrons in the inner shells, because there are 7 electrons in the outer shell, so that gives us an effective nuclear charge of 7+. So as the charge is increasing from left to right, clearly the attraction for electrons towards the nucleus will also increase. So that accounts for an increase in electronegativity. Now, in addition to that, we could also say, and as we've already seen a number of times now, the atomic radius decreases. So as the atomic radius decreases, the electrons that are in the outer shell are now closer to the inner shell, closer to the nucleus. These electrons are this far away from the nucleus. These electrons are only this far away from the nucleus. So because these electrons here are closer, they're experiencing a stronger pull. So both the effective nuclear charge is increasing and the atomic radius is decreasing, and each of these factors result in an increase in the electronegativity. All right, electronegativity in summary increases as you go from left to right across the period. So why was that? Another way of explaining this is to pick specific examples. So elements on the left of the table have 1 or 2 outer shell electrons and would rather give those electrons away to achieve octet, to achieve noble gas configuration, which is stable. So it's easier for them to give those electrons away than gaining electrons from other atoms. And so if they have a tendency to naturally give away electrons rather than gain them, it follows that they're going to have a lower electronegativity. This is not a good examination response. We can't use words like would rather give, grab. These are hardly sound technical terms. They imply that the atoms have a choice, that they have a free will. Of course they don't. The explanation that was described in the previous slide is better, which was to look at the change in the effective nuclear charge and the radius, and using these technical terms, an explanation of electronegativity is much more precise. Why does the electronegativity decrease as you go down a group? Well, elements near the top of the period have fewer electrons to begin with. Every electron, therefore, is experiencing quite a strong attraction to the nucleus. But elements lower down in the periodic table have more shells and have more electrons. And having more shells and more electrons, they're further away from the nucleus and are not as strongly held, so they are more loosely held. So atoms at the bottom tend to lose electrons, atoms at the top tend to gain. And the reason for this, again, was shielding. So if we look at shielding, the concept of shielding, just to remind you of that. So the attraction that this nucleus has for this electron, the pulling in power, is basically due to the number of protons. However, there is a pushing out power, and that's due to this electron, or these electrons that are in all the inner shells. So in this diagram, the nucleus is right in the middle, but there are energy levels, 1, 2, 3 energy levels between the nucleus and the outer shell electron. Now, electrons in all of these energy levels here are between the nucleus and are therefore shielding the nuclear pull. We can describe that as each of these electrons are causing a pushing out power. So the balance between the pushing in power and the pushing out power is the effective nuclear charge. The pushing out power is the shielding. Okay. So as you go down a group, the number of energy levels increases. So this is in 1, 2, 3, 4. There are 4 shells, so it's in period 4. The atom above it would have only 3 shells. So it would be in period 3. And so you can see that this atom has 3 inner shells, so much more shielding than the atom above here that has 2 inner shells, much less shielding. Now, of course, the other thing is that the atomic radius is increasing. So a description of the trend in electronegativity down the group, again, should also consider radius and shielding. But this time, not the effective nuclear charge, because down a group, the effective nuclear charge remains constant. Okay, questions? Which properties of period 3 elements increase from sodium to argon? So as we go from sodium to argon, yes, the nuclear charge is increasing. The number of protons are increasing. The atomic radius, no, is decreasing. The electronegativity, yes, is increasing. It increases from left to right. So the correct answer is 1 and 3, B. Next question. Which factors lead to an element having a low value of first ionization energy? Putting this another way, a low value means the atom very easily ionizes, easily loses electrons. So electrons will be lost easily, definitely, from large atoms. Large atoms tend to have a high number of energy levels. So yes, they will tend to lose electrons quite easily. But a high nuclear charge would tend to hold on to the electrons. So the correct answer is 1 and 2, A. Explain how the first ionization energy of potassium compares with that of sodium and argon. Well, the first ionization energy of potassium will be lower than sodium and argon. We have compared them. Additionally, we could say that argon is the highest of the 3. So we've made a comparison. Now explain. Why is that? Well, looking at the position of potassium in the periodic table, comparing it with sodium, potassium has 1 more shell than sodium, and in fact 1 more shell than argon. So having 1 more shell, it will have a larger radius. There will be more shielding. And as a result, the electronegativity or the ionization energy will be lower. Explain the difference between the first ionization energies of sodium and magnesium. Now, sodium has an effective nuclear charge of 1+. Magnesium has an effective nuclear charge of 2+. The electrons are held more strongly by magnesium. So this implies higher first ionization energy. Question 3, suggest why much more energy is needed to remove an electron from sodium than magnesium. From the sodium ion, rather, than the magnesium ion. Right, well, let's look at the configuration. The sodium ion has a configuration of 1s2, 2s2, 2p6. The magnesium single plus ion has a configuration of 1s2, 2s2, 2p6, 3s1. So I think now you can see why. Sodium has noble gas configuration. This is really stable. Magnesium has neon's configuration up to this point, but then it still has one more outer shell electron, which is held more strongly than the previous electron, than the first electron that was removed, but can still be removed more easily than the second electron for sodium. So removing that electron would then give magnesium noble gas configuration. And that's why the most common magnesium ion is actually the double plus ion. Okay. All right, so that's enough for this video, and the next set of videos we'll start looking at reactivity.